What's up, guys? This is Mr. Barone here. Why don't we just jump right into it? Here's your do now. Read the question. It's all based off of a lab that we did, so this comes straight from the Regents exam. I really like these questions because it proves to you the stuff that we do in my class, it's for a reason. So that lab we did with copper sulfate, where we heated up that blue substance and turned it gray, it is literally from this topic. So why don't you take a minute, read this paragraph, read 66, 67, and 68, and answer as many of those as you can. So pause the video now and go ahead. All right, so this is a bit of a heavy slide here because these questions are not terribly easy to show here. I have to do a little bit of math for each of these, so I'm going to try to cut some corners. Explain why the sample. So first of all, let me take a step back here. You have a hydrate, which is, we talked about hydrates. It's a compound that has water molecules within its crystal structure. We did copper sulfate, pentahydrate. There were 5 water molecules as part of copper sulfate. This is magnesium sulfate heptahydrate, meaning there are 7 water molecules part of the structure of magnesium sulfate. The hydrated compound has 7 moles of water for each mole of magnesium sulfate. When 5.06 grams of magnesium sulfate heptahydrate are heated, the water molecules are released. The sample was repeatedly heated until the remaining MgSO4 had a constant mass of 2.47. During this laboratory activity, appropriate safety equipment was used and safety procedures were followed. Oh, thank goodness. Okay, here we go. Number 66. Explain why the sample in the crucible was heated repeatedly until the sample had a constant mass. So we started out with 5.06 grams of the hydrated compound, and they kept heating it and heating it and heating it until it was 2.47 grams, and it never changed. Okay, why? Number 66 is saying, why did you keep heating it? And so the answer is you just want to make sure you got rid of all the water. That's it. You're going to ensure that there's no water left over in the substance. So my answer for number 66 would be, again, I try to use the question to help formulate my answer. So I would say the sample in the crucible was heated repeatedly until the sample had a constant mass because we wanted to make sure all of the water was removed. That's it. You want to make sure you got rid of all the water, and that's your answer for number 66. That gets you 1 point. Number 67, using the lab data, show a numerical setup for calculating the percent composition by mass of water in the hydrated compound. Well, just like the lab, the mass of the whole thing, the hydrated compound, including MgSO4 and water, was 5.06. After you heated it repeatedly and you only have 2.47 grams left, that's the anhydrous compound. That means we've gotten rid of the water. So this is the mass of the whole thing. Okay, and this is the mass of the magnesium sulfate. This is a bit of a tricky question. They want to know the percent composition of water. So this here is our mass of magnesium sulfate. So we got to do one quick step before we can use our equation. I got to use my phone here for my calculator. So what you're going to have to do is the mass of the whole thing is 5.06. The mass of anhydrous salt is 2.47. So if you subtract that away, whatever's left over should be your mass of water. And that's why it's a bit tricky. You have to use the numbers in the question to get the number of water that you need to plug into a separate equation. So 5.06 minus 2.47, and you should get 2.59. 2.59. And that is grams of water. So you were successfully able to boil away or heat away 2.59 grams of water. And if you ever want to check it, remember, this is your MgSO4. This is your H2O. So if you add them together, you should get something really close to what your original mass was, and you do. Okay, so this makes a lot of sense. But now they want to know the percent composition of water. So the part that we care about is not the magnesium sulfate. That's not the part we care about. This is the part we care about, water, and this is the mass of the whole thing. So according to your reference table, Percent composition, where are you? It's the mass of the part divided by the mass of the whole thing times 100. So the mass of the part divided by the mass of the whole thing times 100. And if you put all that down, you don't even need to calculate it. I'm going to do it over here. So it'll be 2.59 is my mass of the part. 2.59 divided by the mass of the whole thing, which is 5.06. And you're going to multiply all that times 100. That's all you have to put, and you would get full credit. You don't even need to solve it because it just says to show the numerical setup. So that's your answer for number 67. 2.59 divided by 5.06 times 100. Okay? If you solved it, you should get something, I don't know, it looks like about 50%. But, you know, don't even need to solve it. It just says the numerical setup. All right, last but not least, determine the gram formula mass of magnesium sulfate heptahydrate. Well, the good news is you guys are really good at this. This is one of the last things that we talked about in class before we had to go to online learning. But MgSO4, that is your formula. So you just got to do this in pieces here. So MgSO4, if it didn't have the water there, this wouldn't be terribly complex. You have Mg, you have S, and you have O. Sorry, I'm running out of space. You have one magnesium, and each magnesium weighs 24 grams. Sulfur, there's one sulfur, and each sulfur weighs 32 grams per mole. And oxygen, as I run out of space, you have 4 oxygens, and each one weighs 16. So you have 4 oxygens times 16. Okay? So this whole thing should give you a mass of, for MgSO4, bear with me here, it'll be 24 plus 32 plus 64, 120. So you have 120 grams coming from MgSO4, but that's not all of it. We need to know the mass of the 7 water molecules that are attached to it. So H2O, at this point, you guys can follow the same process to know that H2O is 18 grams and that there are 7 of them. So there's, every H2O molecule weighs 18 grams per mole. You can follow the same process. 2 hydrogens, one AMU each, and 1 oxygen for 16. So 16 plus 1 is 18. So every water weighs 18. And there are 7 water molecules. So it's 18 times 7. This is the mass of water that we have to add to it. So let's do this. So we have 18 times 7. We have another 126 grams that come from the water. So my gram formula mass should be 120 plus 126, which would be 246. So my final answer should be 246. Like I said, this is not, it's a brave new world here, guys. You should be able to go check your work. Like if you really care about this stuff and you're really in it to win it and you're really like trying to make this online learning work, see if you're right. Let me go pause the video and see if I can find confirmation that this is in fact our answer. So hold on. All right, so I just did a quick Google image, or Google search for molar mass of magnesium sulfate heptahydrate, and magnesium sulfate by itself is 120. Well, we came up with that. We had 120, but this Google search is not including the mass of the water. So let's just keep looking here, and all of a sudden you see down here that we have magnesium sulfate heptahydrate, and we have a molecular weight of 246, right? And you can totally go Google this and confirm it, but the molar mass of magnesium sulfate heptahydrate is in the neighborhood of 246 grams per mole. And that is, in fact, what we had, 246. All right. So our answers are correct. Moving on. Let's see here. Our objectives. In the earlier video from before, we labeled and quantified all of the activation energy arrows on a PE diagram. Today, we have one last arrow to look at before we have figured out all of the PE diagrams. And that's going to be called delta H. Just like delta T, change in temperature, Delta H will be change in something else as well. So we're going to label the delta H arrow on a blank PE diagram, and we're going to identify its value. We're going to quantify it. All right, here is your meme of the day. There you go. Hopefully you found it funny, because this is all about PE diagrams in this unit, not phase change diagrams. Phase change diagrams are those steps that go up like steps and they go from solid to liquid to gas. Don't confuse those with potential energy diagrams. We have been looking at potential energy diagrams, and we will continue to do so. So here we go. In your notebook, you're going to want to write this down. The delta H. Delta means change in, and heat. H means heat. So delta H literally reads change in heat. It has a couple of other names. You will see it referred to a lot as delta H in this class and on the regions. Change in heat in this class and on the regions, and even heat of reaction on the Regents exam and in this class. It will go by all of those names. It also goes by this name called enthalpy. We do not use that term here in New York State Regents chemistry, but you may see it. Enthalpy is another name for this as well, but we do not use that in this class, so you don't need to worry about that. But know that delta H means change in heat or heat of reaction. You need to be familiar with all of those terms. So here you go. That green arrow represents the delta H. Can you figure out what value you think it would be in kilojoules? Do you think you can figure out how to determine the delta H? What's the rule for finding it? So why don't I pause the video now? Why don't you guys try to think about the answer to these questions? Go ahead. All right. So delta H is not that bad. Like I said, none of these arrows, whether it's the PE, the potential energy arrows, or the activation energy arrows, none of them individually are that bad. But when you put them all together, it can be overwhelming. There's a lot to remember. And delta H is another one of those where there can be some small mistakes that you make along the way. I would imagine that most of you guys feel like you can quantify the value pretty easily. You're probably thinking something like 20 kilojoules. As for the rule, maybe fewer of you guys think you can come up with a rule. But the rule is going to be this. Not that. This. Okay? The difference between the potential energy of the products and the potential energy of the reactants. In other words, you're going to take the potential energy of the products, and from it, you're going to subtract the potential energy of the reactants, and that value will give you the delta H. Now, I want to highlight this here. If your delta H is positive, it's endothermic. If your delta H is negative, it's exothermic. We started to see this now. We're going to sort of come back full circle from one of our earlier lessons on this topic. Now we have an actual surefire way to prove whether or not we have an endo or an exothermic reaction. And it's all going to be about quantifying the value of delta H. Okay? So the important thing is, as I go back to your turn and talk, it's always got to be products minus reactants. So if I wanted to figure out the rule for this, it's going to be products minus reactants. And suddenly now in this type of question, you can see why the sign, whether it's positive or negative, is so important. So for this question here, if the rule is, it'll be the PE of the products minus the PE of the reactants. And that equals delta H. That's our rule according to what we copied down in our notes. So if that's the rule, well, the potential energy of the products is 20 minus the potential energy of the reactants is 40, right? It's 40 right there. So 20 minus 40 is going to equal our delta H. Well, now you see why the sign is so important. So that's going to equal delta H. And in this case, in this question, that'll be negative 20. And that negative sign means something very important. So our answer to this is negative 20 kilojoules will be our delta H. Okay? And that equals delta H. So now, knowing that what we just saw before, couple of different ways you can solve this, but going back to one of our earlier lessons in this series of lessons on these graphs or these diagrams, you know that this is higher than that. It's going down. And when you end with less energy than what you started with, you'd say that it's exothermic. And now you also know it's exothermic because it has a negative 20 kilojoule delta H. Any negative delta H is exothermic. And what we're going to say is that this reaction is releasing energy. It's releasing 20 kilojoules of energy, and it's exothermic. All right? So going back. Again, if you didn't do it already, pause it. This is a super important slide. You have the rule for calculating delta H. You have whether or not it's endothermic or exothermic. If it's positive delta H, it's endothermic. If it's negative delta H, it's exothermic. And you have the like sort of definition of what this value means. It's the difference between the potential energy of the products and the potential energy of the reactants. So I'll go back again. Like I said, sorry, I didn't prompt you guys. If you want to pause it now, copy these down. Okay. The second thing you might want to copy down are the actual steps. Some of you guys are like, good, Mr. Barone, I get it. I don't need any more details. But if you want like concrete steps to follow, I always find the potential energy of the products first, write it down. Then I find the potential energy of the reactants and I write it down. I always subtract products first and then I get my answer. Okay. So I will let you guys try this. Why don't you pause the video, copy this in your notes, fill it in, and see if you guys can figure it out. All right, welcome back. So following the steps, find the potential energy of the products first. It's funny. So the products, here are my products. Okay, and think about all the different little things you need to know to make this work. You need to know potential energy goes from here to here. This is my potential energy arrow. Right? You need to know that this is my product side. So I know that the potential energy of the products is 100. Okay. I also know the potential energy of my reactants is going to be, we'll do it in green, is right here. So this is my potential energy of the reactants arrow. That goes here. And that's only 50 kilojoules. Okay. Now I will do the delta H arrow as well in blue. So the rule is it's the products, potential energy of the products minus the potential energy of the reactants. In this case, it's 100 minus 50. It will be positive 50. Okay. And if I want to draw the arrow, it actually is represented right here. So that arrow, the delta H arrow, goes here. Notice it goes from this line to this line. Okay, so there's my delta H arrow, and it represents 50 kilojoules. It's positive because the products have more energy than the reactants. Therefore, it will be endothermic. So I'm going to write this in a complete sentence. The following reaction is endothermic because it has a positive delta H. You could say the following reaction is endothermic because the products have more energy than the reactants. You could even say that it's exothermic because you end with more energy than what you started with, or it absorbs energy. Any of those things would be sufficient. But a positive delta H tells you that you did absorb energy. All right, let's try a few more, and then we'll give you guys your exit slip. Why don't you take a minute and answer this question? Pause the video and give it a shot. Okay, welcome back. Let's get right to it. Again, the potential energy of your products. In this case, potential energy of my products goes here. That value is 10. There are no units there, but will almost always be kilojoules. So it will be 10 kilojoules for my product. My reactants will be, what color did I make it? Blue, green, blue, green. Okay. My reactants will go from here to here. This is my potential energy of my reactants. That's what that arrow represents. Going back to the first lesson on these diagrams, that represents 30 kilojoules. Suddenly you see now that my reactants have more energy than my products, meaning the bigger number is subtracted on the bottom, meaning it should be negative, and that will be the case. The rule is my delta H is my potential energy of the products minus the potential energy of the reactants. 10 minus 30 should be a negative 20. kilojoules. Okay, so it's a negative 20 kilojoules. And remember, it goes from here, from the potential energy of the products to the potential energy of the reactants. Most of the time, this arrow is drawn floating around here in the middle. But again, it could be anywhere. You could draw this line here too if you wanted to. It represents the same magnitude. You could draw it all the way over here. Don't be confused by where the arrow is drawn. It's the values that it indicates from end to end that really matters. All these blue arrows represent the same value of delta H, and it's negative 20. So this reaction will be exothermic. How do I know? The following reaction is exothermic because it has a negative delta H. Probably the easiest answer. This reaction is exothermic because the products have less energy than the reactants. Also true. This reaction is exothermic because this reaction gives off energy. That works as well. These all will work. All right. There's the baby. All right. So here we go. You guys can fill out this exit slip online. I will post it on a Google Doc, and I look forward to seeing your responses. Our objective between yesterday's lesson and today's lesson were to label all the AE arrows, to identify all the AE values, that's activation energy. Now you know how to label the delta H arrow and to identify the delta H on a diagram, on a PE diagram. And also you should know now how to explain whether something is in fact exothermic or endothermic. All right, guys, that's it. Again, make sure you go to Google Classroom and turn in your exit slip at the end of this lesson. Have a great day.